Thank you all for being here. My name is Ruud van der Pas. I work in the Oracle engineering organization as one of the performance people. Today I primarily want to talk about how to optimize for a NUMA system. Before we do that, I need to show this safe harbor statement. I'll do that quickly. It'll be recorded and people can stare at this as long as they like. I want to say a few words about Oracle Linux. I'll keep that very short, but I think too many people are not aware of it, and it's really cool. Then I'll talk about what a general modern system looks like today. Then I'm going to talk more about NUMA and data placement, OpenMP support for that, and finally a performance tuning example. Yeah. Like I said, this is very short. I'll keep it short. It'll be recorded, and if you want more information, it's all available. We do have a very nice Oracle Linux implementation. It's been around there for quite a long time. It's 11 years since we started doing it. And what I'd like to point out, it's fully compatible with Red Hat. And it's a fully supported product. It's not some grassroots effort. It's a real product. And so we have support in place, we have development in place, everything that you would kind of expect from a company like Oracle. What I'd like to mention, because few people know that as well, we actively contribute back to the community. We do a lot of our own development. We have a kernel engineering team. We have different engineering teams. I said I'm on the performance side, so if you find something, we'll fix it and we'll put it back. Okay. If you like to give it a try, here's the download side. Again, these are the binaries. You can just download them and use them. If you like to get the source, it's fully open source. So we're on GitHub. And very few people know that, I think. You can just get our sources and see how things work under the hood. All right, that was a little bit about Oracle Linux. I'll be more than happy to talk more about it after this talk. I'll be in the booth for another 2 hours. I want to talk about NUMA. What does a typical, what I call generic NUMA system look like today? And and I started moving away from the word socket, as I'll explain later. Here we have a system with 4 NUMA nodes. And each node is kind of identical. Each node has a bunch of cores, a bunch of caches, including a last level cache, typically L3 these days, a level 3 cache, that is shared among the cores. And there's memory. And the whole key thing is that the path from the processor to the memory is cache coherent. So what we do, or everybody does, you connect those nodes through a proprietary cache coherent interconnect, and that differentiates it from a cluster. And I'm sure you're all familiar with that. I just want to make sure that I've covered this. To the developer, this is sort of what I think it looks like. What you have your threads. They run on that system, in this case 4 nodes. Your data is somewhere, and through some magic, you can access any data location anywhere in the system. And technically, that's the cache coherency that takes care of that. So here's the NUMA view. Memory, although it's physically distributed, it's logically shared. It means, what does it mean? It means that you can access any memory location anywhere in the system, and it's accessible to all the threads. The thing is, you don't know what the data is, and some people say it doesn't matter. Well, unless you care about performance, and that's what I'll be talking about. You better take care of it. So, same picture. Here's the situation. When you're executing your thread up there on the left, upper left node, then the question is, where's your data? If you manage to organize it so that your data is in that local memory, then you're in business. That's the fastest memory access you can get. In the worst case, it's like this. You're executing your threads here, and in a faraway corner of the machine, your data is there. And you'll get it. The hardware will take care of it. There's no software needed, but it'll take longer. And even if you have part of that when you run multi-threaded, and some of your accesses are local and others are remote, you'll still typically get slowed down by the longest memory access, certainly until you hit the next barrier. I need to have a little bit of terminology. The word thread is somewhat overloaded. When you look at the thread from a hardware point of view, the hardware designers often call it a strand. And I'll use that word, so when I say thread, it's software. When I say strand, it's hardware. Just to make things a little, hopefully less confusing. And so that's what I'll be doing. Technically, a strand has a unique idea in the system, and it has some state, like registers and maybe some cache associated with it. I won't talk about it at all. To us, it's like the hardware versus the software. Gosh. The interesting thing is in Linux, and I hope you're all familiar with it, there's a command called lscpu. Just a show of hand, who's familiar with that command? All right, several of you. All right, good. That will show you in what way the system is organized. And here's an example. I type in lscpu, and I get a whole bunch of output. But to me, for this kind of tuning, I want to look at the NUMA nodes. And what it tells me, there are two NUMA nodes, 0 and 1, so that we know. Each NUMA node has 26 cores. Well, how do I know that? These are, the comma-separated lists are strands. So what we see, there are two strands in each core, and in total there are 26 cores. So that's what we know. So that's how to read these kind of numbers. And we'll see the numbers are 0 to 25 for the first strands in the first node, and then they continue to 26. So strand number 26 is in my other socket. That's what it tells me. And so if you reference 0,52, you'll have the first strand in the first core and the second strand in the first core. It's a little tricky. When you've stared at it long enough, it starts to make some sort of sense, but okay. There's another command that I find really useful. It's called NUMA control, and with the -H, it'll echo you all the numbers and some other information, but I'm interested in the latency table. And these are relative latencies. Then for some practical reason, they're normalized to 10 on the diagonal. And what it shows you is that there's the other node, there's a cost in accessing that memory. Now, practical tip, don't read this too accurately. Don't read this as this is 2.1 times more expensive. I don't think you can say that. But it's clearly there's a higher cost going to your other node. That's what it says. All right. So those two commands are kind of, I always type them in way too often. All right. So with that information, we can reconstruct what our system looks like. What it looks like, we've seen there are two nodes, each with their respective memory, and one of the information given, extra information given, is the size of the memory attached to a node. So you know how much memory there is. There's definitely memory. And there are 26 cores and 52 strands in each, and these are the numbers. All right. And again, notice the jump. From 25, you go to 52. And the reason is then that makes it easier to get all the strands across all the cores, because that's 0 to 51. And actually, surprisingly often, that's what you end up using more than the other way. So I think it makes sense. Okay, so that's the hardware side. Now let's look at data placement. The question is, how do I control where my data goes? Okay, and that's kind of the key part of this talk. How do I know where my data is, and how do I control it? And what all operating systems use, as far as I know, Windows, Mac OS, they all use what is called first touch data placement. And what the simple version is that the thread that touches your data for the first time owns it. That dictates the location. And that's sort of, unless you copy things around or explicitly move data around, that's going to be the home node of that data. So it's a very crucial stage. And I'll get back to that. But you want to make sure that that's where things are done the right way. It makes sense to have this as a default. Oh, I'm really sorry. Sorry, Richard. It makes sense because this behavior preserves sequential execution performance. Because when you run a single thread, you want to have your data close to your memory. And there's only one thread touching the data. So this is a very logical sense, makes sense, but it's not so good for parallel computing. It works fine, but what if a single thread initializes your data? And most people are not aware of it. This is why I decided to talk about it. Then, as you should all know now, all your data will be in one memory. Unless it doesn't fit, then it will overflow through some nearby memory. Not only does that increase the access time for the threads that are executing elsewhere, you could potentially also have a bottleneck at that memory controller because all threads are going there. Luckily, the solution is often surprisingly simple. So how do we do that? You parallelize the data initialization part. And in that way, you kind of force the system to spread your pages over your nodes. And here's a very simple example. I initialize my vector to 0. If I wouldn't do that with OpenMP, then again, one thread would own all the data. So a very simple parallel 4 will do the magic. As you probably all know, that means the iterations are distributed over the threads, so they all get a slice of the data. I do use the static, because the default is system dependent. You don't want to have this like done in a dynamic way. That defeats the whole purpose. Unless a special case, okay? So be careful with that. I would, to be safe, maybe up to the paranoid level, use schedule static and do it that way. All right. And in that way, you distribute the data. So the way you do that in practice is that you look at how your algorithm accesses the data, and you do some reverse engineering, like, then I have to massage my initialization in such a way that it'll end up mostly in the right place. I don't think, unless it's a very simple case, I don't think you can strive for optimal placement, but you can ease the pain. All right. So don't be discouraged if you can't get the optimal location everywhere. That would be too good to be true. It's only the case in my demo. So, all right. Okay. Now, luckily, since 4.0, OpenMP supports NUMA, and that's really a big step forward. And anybody using that here? Yeah? No? Okay. Okay, good. So you may have the nasty questions. Please start looking into it either after this talk, or I hope it encourages you to take a look at it. And let me explain it. Okay. The idea is the following. The data is wherever it is. What we're going to do, we're going to move the thread to where you say it has to go. And the reason is moving a thread is a lot cheaper than moving data. All right? So your kind of responsibility is to make sure that the data is in a location where you'd like it to be, like using First Touch. And then through the OpenMP controls, you specify where the threads will run. And I'll show you, there will be examples. There are two environment variables to control this. All right. One is called OMP PLACES. And with that's a list. And a list that defines where your threads are allowed to run. So yes, you can exclude places, locations. You can say, I don't want you to run there. I want you to only run in this part of my machine for some reason. Yeah. And then you use the PROC bind environment variable to specify how the threads are going to be mapped onto those places. I see some puzzled faces. I'll show some examples, but that's the general idea. So it's a two-step approach. Okay. When you do this, really use this environment variable, OMP underscore display underscore env, it will echo your settings. So it's a sanity check. And in case you've made a mistake, which of course never happens to me, but it may happen to you, then it will tell you that, oh, I go to the default because you have a type, you have some error in your definition. Please use this environment variable, set it to verbose, and before your program starts, it will echo all the environment variables. Very useful. So let's look at some examples. Let's say I want to schedule all the threads on the cores in my system. Well, what I can do, I can say the places are the cores in my system. It's as easy as that. Yeah. And you want to spread them out. You want to leverage the bandwidth. You don't want threads to be literally close to each other. You want to spread them. You say proc bind equals spread, and then the runtime system will make that happen. Right. You have more choices than that. There's sockets, cores, threads, and a user-defined set to give you full control. There's an optional number n that you can use to say how many cores you'd like to use. Like I have 8 cores in my system. I only want to use 2. That's how you do that. Same for threads, sockets, cores, and threads. You can all limit how much you want to use. And that defines the places, like all the sockets, all the cores, and so forth. Personally, I end up using the user-defined set most of the time, and that's what I'll zoom in on. But be aware there's this high-level symbolic notation as well. Okay, let's say we want to schedule onto the sockets. All we do is this. All right. But let's say we want to use, for some reason, I want to use strand 0, 8, 16, and 24. All right. You define your list this way. Each entry between the curly braces is a place. And I can have more than one number. Here I'm showing one number, but it's set-based. It's a set of sets in a way, what you define. So here's very simple. I have 4 places, and those should be used. So how about the placement policy, where the threads are going? You've got 3 choices. And there's no user-defined choice for that, by the way. It's either master. Master means it's especially useful with nested parallelism, where you have multiple master threads in a way. You want to keep the threads in that group close to their master. So that's I think the only realistic use I can see for this feature. Most cases people use close or spread, where you either keep the threads close or spread. And the most common usage of that is when you have 2 loops. And what you want to do, you want to have like the outer loops spread over the machine, and then within that parallel region you want to keep them close. Something like that. You can mix and match. Okay. So how do you do the places on our imaginary, no, it's not even imaginary, it's a real system with these numbers that I showed in the beginning. Let's say for the fun of it, I want to use the first strand on each core in the first socket. All right. I'm not a big fan of asking questions to the audience unless it's a simple hand waving, but you got to look at these numbers. So let me, in interest of time, let me show you the result. So what I have here is 0, 1, up to 25. So I have 26 places, and that's exactly this list here. Those are the first, this is the first NUMA node. Those are the cores in that node, and I want to use the first thread there. That's a long list. It's a lot of typing. So luckily there's a compact notation, very powerful, where I have the starting point, 0, strand 0. I want to have 26 places and an increment of 1. So that expands to this list. And that's a way more convenient notation. Okay. So again, start idea, number, how many you want to have, and the increment. And that could be anything. Another example, for some exotic reason, I want to have the first strand in the first part of the machine and the second strand in the first 4 cores and the second strand in the first 4 cores in the other socket. Well, you can imagine what that looks like. That's something like this. And if you've never seen this before, it takes a while to get used to, but eventually you actually find it easy. So that's how I like to use it, because it gives me full control. All right, let me finish with a performance tuning example. My favorite algorithm, it's extremely simple, and there's actually a lot to say about it. It's multiplying a matrix with a vector. Here's one way you could write it in C, taking the dot products of the row of the matrix times the vector, and you do that for all the rows, and you have your result. It's almost embarrassingly parallel, because all these dot products are independent. All right? So that's how you would do that with OpenMP. And by the way, every self-respecting auto-parallelizing compiler will do this for you. So if you have that, they probably do the magic for you. I just want to illustrate this. I used an AMD EPYC server with 2 sockets. The reason is that for this kind of talk, it's a great kind of lecture machine, because it has, although it has 2 sockets, it has 8 NUMA nodes. So it's sort of NUMA within a socket. And that allows me to play a little bit with this stuff. You check that with LS-CPU, as I showed. And you also find out each NUMA node has 8 cores and two strands each. So in total, a 2-socket AMD EPYC box, the high end, I must say, has 64 cores and 128 strands. So LS-CPU now is a little more interesting sort of output. It'll give you all these numbers, and you'll see the latency table for all the 8 nodes. So what it says is that when I'm on node 0, there's a cost going within my socket to node 1, 2, or 3. And there's a higher cost going off socket. Okay. Now the off socket part is fairly conventional. The in socket is a little less conventional, but that's just the way it is. And this is how you find out. Okay. My setup, I didn't use the second thread, by the way, because for these very CPU intensive programs, there's no use for that second thread. So I want to distribute my threads across all those cores, all those 8 nodes. So I want to have 8 threads, each node has 1 thread, and then I'll have 2 threads. In that way, I maximize the bandwidth in my system. All right? That's why I did it that way. All right. So this is an example. And here's what my settings look like. And the list starts to get long. It's about as long as it can get for this 8-node system. I'm still a little bit struggling to see if I can make it more compact, but I haven't found that yet. So this is as tight as I can get it. I define my places. Again, 2 threads in this example. And so this is the first NUMA node. I want to have 2 threads, so it will be 0, 1, 8, 9, 16, 17, and so forth. That's how it will be expanded under the hood. I want to keep my threads close to each other, and just for sake of the example, these are 16 threads that I'll be using. So that was my setup for my experiment. Here's the performance as a function of the number of OpenMP threads. And remember, I have 128 strands, but I'm only using half of it. The performance in gigaflop, so higher is better. This is very, very poor performance, the reddish line. And the reason is I didn't do first touch. I just had a simple sequential function to initialize my matrix and my vector, and it shows. All right. This one uses first touch, and I didn't really have the time to show you the code, but I'm happy to talk about it offline. It's actually fairly simple. It's no magic here. You just have a bunch of parallel for loops when you initialize the matrix and the vector. So now I get, this scaling is so poor I didn't even attach a number to it. Here I got 35x. It has some interesting behavior here which I haven't analyzed yet in this plateau, but ultimately the speed up over the single thread performance is 35x. Altogether, by using first touch, I get 22x performance improvement on the same hardware. And I hope that number is high enough to convince you to start looking into this. All right. So some conclusions, fairly obvious. I think data and thread placement really matters, and it could be matter a lot. All right. It's really very powerful to leverage first touch. It's generic. I can take my code and run it on any architecture, and it'll automatically expand to do the right thing. The one thing I probably want to do is adjust my places definition for that architecture, but the code, the binary itself, will just run. And that's because first touch is such a general principle. Right. I think the support in OpenMP, given how close this is to the hardware, is very elegant and powerful. And more has been added in OpenMP 5.0. So maybe next year I can talk about that in more detail. This is the lawyer talk. So thank you very much. I welcome questions.